Welcome! In this session, we'll be exploring LeetCode problem number 2137. While the exact problem title and details are unavailable, we'll analyze potential strategies based on common algorithmic patterns. Let's dive in and uncover insights together. At this time, we are unable to provide the detailed problem statement, examples, and constraints for LeetCode problem number 2137. To view the complete details, please refer directly to the problem page on LeetCode at the provided URL. This issue might be due to temporary unavailability or restricted access to the problem's metadata. When tackling any algorithmic problem, it's useful to start by considering the range of possible approaches. The brute force method is often the most straightforward starting point. Here, the goal is to exhaustively evaluate all possible solutions, such as iterating through every combination or testing all scenarios. This method can be implemented using nested loops or recursion, making it relatively simple to construct. However, the trade-off for this simplicity is inefficiency. Brute force solutions typically have high time complexity, often exponential or polynomial, which means they quickly become impractical as the size of the input grows. While this approach is rarely the final answer, it is valuable for validating the problem's logic or as a baseline for comparison. After this, we can explore more optimized strategies such as divide and conquer, dynamic programming, or greedy algorithms to improve efficiency and reduce redundant calculations. Optimized approaches aim to address the inefficiencies of brute force by leveraging patterns or properties in the problem. For example, dynamic programming is particularly effective when overlapping subproblems exist. By storing intermediate results using techniques like memoization or tabulation, we avoid recalculating solutions, significantly improving time complexity. In problems with an optimal substructure, greedy algorithms offer another option by making locally optimal choices at each step, which can lead to a globally optimal solution. For other problem types, specialized methods like binary search or graph algorithms, such as breadth-first search or depth-first search, come into play. These techniques are designed to exploit specific properties, like sorted data or graph connectivity, to solve problems efficiently. While these methods often deliver the best performance, they require careful implementation and may not always be applicable. For this hypothetical problem, we lean toward dynamic programming, as it balances efficiency and adaptability to a wide range of scenarios. Dynamic programming is a powerful approach because it strikes a balance between simplicity and efficiency. Unlike brute force, it avoids exponential growth in computations by breaking the problem into smaller subproblems and reusing their solutions. This makes it particularly suitable for problems involving sequences, pathfinding, or optimization tasks, where overlapping subproblems are common. However, it's important to consider the trade-offs. While dynamic programming guarantees correctness in cases where greedy algorithms might fail, it typically requires more memory. On the other hand, compared to graph-based strategies, dynamic programming is often easier to implement for linear or one-dimensional problems. When assessing the best approach for a problem, the constraints and input size play a critical role. For smaller inputs, simpler methods like brute force might suffice, but for larger inputs, more efficient strategies such as dynamic programming or divide and conquer are essential. The goal is to balance runtime efficiency with the complexity of implementation to find the most practical solution for the given problem. We are tackling a minimum cost path problem in a grid. The goal is to find the path from the top left corner to the bottom right corner that minimizes the sum of the costs in each cell traversed. To solve this efficiently, we use a dynamic programming approach. First, we initialize a DP table where each cell will store the minimum cost to reach that position. We set the starting cell, DP 0, 0, to the cost of the top left corner, grid 0, 0. For the base cases, we compute the cumulative costs along the first row and the first column since there is only one way to reach those cells, from left to right for the row and from top to bottom for the column. For the first row, the cost to reach any cell is simply the cumulative sum of costs from the top left corner. Specifically, for each cell in the row, we add the cost of the current cell to the cost of the cell to its left. Similarly, for the first column, the cost to reach any cell is the cumulative sum of costs from the top left corner downward. Here, each cell in the column is calculated as the sum of the current cell's cost and the cost of the cell directly above it. Once these base cases are handled, we move on to filling the rest of the DP table. For any other cell, the minimum cost to reach it comes from the smaller of two possible paths, the cell above it or the cell to its left. We add the current cell's cost to the minimum of these two values to compute the total cost for that position. The final result will be stored in the bottom right cell of the DP table, which gives us the minimum cost to traverse the grid. This approach avoids redundant calculations by leveraging a DP table, where each cell is computed only once. The overlapping subproblems, like the repeated calculation of costs for shared paths, are resolved by storing intermediate results in the table. This ensures an efficient solution. Now, let's discuss the data structures and complexity. We use a DP table to store the minimum costs, which has the same dimensions as the grid, mxn. The input grid itself represents the cost of traversing each cell. The time complexity is O, m*n, because we fill each cell in the DP table exactly once. The space complexity is also O, m*n, due to the DP table, but it can be reduced to O, n, by storing only the current and previous rows of the table. Additionally, we can optimize further by using early termination if constraints like a maximum cost threshold are specified. When implementing this algorithm, it's important to handle edge cases effectively. For a single-cell grid, the result is simply the cost of that one cell. If negative costs are permitted, the algorithm should account for this while maintaining correctness. For an empty grid, we return 0 or handle it as invalid input. For very large grids, we need to ensure that the algorithm can manage memory constraints efficiently, especially if the full DP table is used. Let's walk through an example to solidify these concepts. Given the grid 1, 3, 1, 1, 5, 1, 4, 2, 1, we begin by initializing the DP table. The top left corner is set to the cost of the first cell, 1. Next, we fill the first row with cumulative sums, resulting in 1, 4, 5. Similarly, we fill the first column, producing 1, 2, 6, when considering cumulative sums downward. Now, we calculate the minimum costs for the remaining cells in the grid. For example, cell DP 1, 1 is computed as the sum of grid 1, 1 and the minimum of the costs from the cell above and the cell to the left, resulting in 6. Continuing this process for all remaining positions, we fill the DP table. The final table looks like this: 1, 4, 5, 2, 6, 7, 6, 8, 8. The value in the bottom right corner, DP 2, 2, is 8, which is the minimum cost to traverse the grid from the top left to the bottom right corner. This demonstrates the effectiveness of the dynamic programming approach in reducing redundant calculations and systematically solving the problem. The code implementation for this algorithm starts by initializing the DP table and setting the starting cell. We then fill the first row and column with their cumulative costs, followed by iterating through the rest of the grid to compute the minimum costs for all other cells. Finally, we return the value in the bottom right corner of the DP table, which represents the minimum cost to traverse the grid. This concise implementation captures the essence of the dynamic programming approach, ensuring both clarity and efficiency in solving the problem. Here, we're implementing a solution to find the minimum path sum on a grid using a Dijkstra-like approach. First, we import the heap library, which will allow us to use a priority queue. Inside the solution class, the min-pathsum method initializes the grid dimensions, and we define the possible movement directions as down and right. A priority queue, PQ, is initialized with the starting point of the grid, which includes the cost at the top left corner and its coordinates. We also define a visited set to keep track of the cells we've already processed. The main logic is within a while loop that continues until the priority queue is empty. Each iteration pops the cell with the smallest cost, and if this cell is the bottom right corner of the grid, we simply return the accumulated cost as the answer. If the current cell has already been visited, we skip further processing for it. Otherwise, we add it to the visited set and explore its neighbors. For each valid neighbor, we calculate the new cost and push it into the priority queue, ensuring we only process unvisited cells within the grid boundaries. Finally, we include a return statement outside of the loop to handle any edge cases, though logically this point should never be reached. The return value of -1 acts as a safeguard to indicate something went wrong if the algorithm fails to find a path. This completes our Python implementation, which efficiently calculates the minimum path sum using a greedy approach with a priority queue to always extend the least costly path first. Here, we are implementing a solution in Java to find the minimum path sum in a grid. We start by importing the necessary packages and defining our solution class. Inside the class, we have the method minPathSum, which takes a 2D array grid as input. The first step is to determine the number of rows and columns in the grid. Then, we define an array directions to represent the possible moves, either going down or moving right. This is important because the problem restricts our movement to these two directions. Next, we initialize a priority queue to help us implement a Dijkstra-like algorithm. The priority queue will store arrays where the first element is the cost, followed by the row and column indices. Initially, we add the starting point, which is the top left corner of the grid, to the priority queue with its associated cost. We also create a 2D Boolean array visited to keep track of which cells have already been processed. Inside the while loop, we repeatedly poll the top element of the priority queue, which gives us the current cell with the lowest cost. We extract the cost and the row and column indices of the current cell. If we have reached the bottom right corner of the grid, we return the accumulated cost as the result. This is because reaching this cell signifies that we have found the minimum path sum. However, if the current cell has already been visited, we skip it to avoid redundant calculations. Otherwise, we mark it as visited and proceed with the algorithm. Now, the algorithm continues by exploring the neighbors of the current cell. For each direction in the directions array, we calculate the new row and column indices by adding the direction values to the current cell's indices. Before adding these neighbors to the priority queue, we ensure they fall within the bounds of the grid and have not been visited yet. If these conditions are satisfied, the neighbor is added to the priority queue with its accumulated cost, which is the current cost plus the value of the grid cell at the neighbor's position. This ensures that the priority queue always maintains the cells in ascending order of their path cost. The loop continues until the priority queue is empty. At this stage, the function includes a return statement of -1 as a fallback, although logically this point should never be reached if the input grid is valid. This implementation effectively uses a Dijkstra-like approach to find the minimum path sum in the grid, leveraging the priority queue for efficient cost management and the visited array to avoid revisiting cells. To begin solving the problem, we take the given grid and initialize key variables. Here, rows and cols are set to the dimensions of the grid, which are both 3 in this case. The directions array defines the possible movements, down and right. We also initialize the priority queue, PQ, with the starting position, 0, 0, and its corresponding cost, which is the value at the top left corner of the grid. As we proceed, the while loop pops the smallest cost element from PQ. Initially, that's 1, 0, 0, where the cost is 1, and the coordinates are 0, 0. We mark this cell as visited and explore its neighbors. Moving down to 1, 0 adds a new path to the queue with a total cost of 2, and moving right to 0, 1 adds another path with a cost of 4. Both of these are pushed into the priority queue, and the algorithm continues to the next steps. Next, the algorithm pops the smallest cost from the priority queue. This time, it's 2, 1, 0, where the cost is 2, and the coordinates are 1, 0. We add this cell to the visited set and explore its neighbors. Moving down to 2, 0 results in a total cost of 6, and moving right to 1, 1 results in a cost of 7. Both of these paths are added to the queue. The process continues, with the algorithm always selecting the path with the smallest cost. Eventually, the bottom right corner, 2, 2, is reached with a total cost of 7. This value is returned as the output for example 1. By following this systematic approach, we ensure that we find the minimum cost path. Moving to example 2, we now consider a single row grid. For the single row grid, we again initialize rows, cols, and the priority queue. Here, rows is 1, and cols is 4, reflecting the grid's dimensions. The initial state of PQ contains 1, 0, 0, representing the top left corner. The algorithm pops this element, marking 0, 0, as visited and exploring its neighbor to the right, 0, 1, with a total cost of 3. This process repeats, moving right to 0, 2, and then 0, 3, updating the total cost at each step. The algorithm terminates upon reaching the bottom right corner, 0, 3, with a final cost of 10. This output demonstrates how the algorithm handles grids where movement is restricted to a single direction, in this case, horizontal. Let's now explore example 3, a single column grid. In the single column grid, the initialization is similar. Here, rows is 3, and calls is 1. The priority queue starts with 1, 0, 0, corresponding to the top left corner. Popping this element reveals a cost of 1 at 0, 0, which is added to the visited set. The only possible movement is downward, so the algorithm pushes 3, 1, 0 into the queue, representing the next cell with an accumulated cost of 3. This pattern continues, processing 1, 0, and 2, 0 sequentially until the bottom right corner, 2, 0, is reached with a total cost of 6. This example highlights that the algorithm adapts seamlessly to grids with restricted movement, such as purely vertical paths. Across all examples, a few observations stand out. The priority queue ensures the smallest cost path is always explored first, cells are visited only once to avoid redundant processing, and the algorithm terminates as soon as the bottom right corner is reached, guaranteeing an efficient solution. To analyze the time complexity of the algorithm, we start by considering the grid dimensions, where the grid has m rows and n columns. The algorithm uses a priority queue, or min heap, to store tuples representing the cost and coordinates of each cell. Every cell in the grid can be added to the heap at most once, resulting in a total of m*n push operations. Now, each push or pop operation in the heap has a time complexity of O log k, where k is the number of elements in the heap. In the worst case, the heap can contain all m*n cells, so the cost of each heap operation becomes O log m*n. When we sum the costs of all these operations across the entire algorithm, the total complexity for heap processing becomes O m*n log m*n. Additionally, for each cell, the algorithm explores its neighbors. The number of neighbors is limited to 2 due to the constraints of the directions array, making neighbor exploration O1 per cell. Since there are m*n cells, the total cost for this step is O m*n. However, since the heap operations dominate the overall runtime, the time complexity of the algorithm is O m*n log m*n. Now let's evaluate the space complexity of the algorithm. First, there's the visited set, which keeps track of all cells that have been processed. In the worst case, all m*n cells are visited, meaning the space used by the visited set is proportional to O m*n. Next, the priority queue, or min heap, can also store up to m*n elements in the worst case, so its space usage is also O m*n. Lastly, the input grid itself requires storage space, which is again O m*n. When we combine these contributions, the overall space complexity is determined to be O m*n. This space usage is quite efficient, as it grows linearly with the size of the grid. Let's break down the best, average, and worst case scenarios for the algorithm. In the best case, the bottom right corner of the grid is reached quickly because the grid weights are minimal. However, even in this scenario, the heap operations still dominate the runtime, making the complexity O m*n log m*n. In the average case, the algorithm processes all cells, and the time complexity remains the same as analyzed earlier, O m*n log m*n. Similarly, in the worst case, where all grid cells must be processed due to high weights, the algorithm still adheres to this asymptotic complexity. To put this into perspective, a brute force approach would involve exploring all possible paths through the grid, which would result in an exponential time complexity of approximately O(2)m+n. This is a significant improvement over brute force, as the current algorithm uses a priority queue to process cells in increasing order of cost, avoiding redundant computations and reducing the exponential runtime to O m*n log m*n. To solidify our understanding, we can provide a mathematical justification for the logarithmic factor in the time complexity. Each cell in the grid is processed exactly once, and every push or pop operation in the heap takes O log m*n. Therefore, the total time complexity of the heap operations across all cells is O, m*n, log, m*n. As for space complexity, the primary contributors are the visited set and the priority queue. Both of these structures scale linearly with the number of cells in the grid, resulting in a space complexity of O, m*n. This mathematical reasoning confirms that the algorithm is both time-efficient and space-efficient given the constraints of the problem. When tackling LeetCode problems, there are a few common pitfalls to watch out for. First is misunderstanding the problem statement. This often happens when we skim through the constraints or miss key details about edge cases. For instance, if the input allows negative numbers or zeros, but we assume only positive integers, it could lead to runtime errors or incorrect results. To avoid this, always revisit the constraints and ensure your solution accounts for scenarios like empty inputs, single elements, and extreme values. Another mistake is overlooking edge cases, such as arrays of size 1, duplicate values, or special patterns like all elements being identical. Designing test cases for boundary conditions early in the process can help. Finally, many solutions fail on large inputs because they aren't optimized for efficiency. A naive approach that works for small test cases might time out on larger ones. To address this, analyze the problem's constraints and estimate the required time complexity. Look for opportunities to optimize with better data structures, like heaps or hash maps, or algorithms, such as divide and conquer techniques. Another common challenge is choosing the wrong data structure. For example, using arrays to find unique elements can result in inefficient nested loops, while a hash set would be a much better choice. To avoid this, focus on the operations you need. If you require fast lookups, sorting, or other specific functionalities, select the data structure that provides these efficiently. Another issue arises when the output format is incorrect. Even if your logic is perfect, submitting a solution with the wrong format, like returning a data structure instead of a string, can lead to rejection. Always double-check the problem's output requirements and match your solution to those specifications. A small oversight in verifying the format can undo all your hard work, so this step is critical. In interviews, recognizing patterns in problems can be a game changer. Many challenges are variations of common techniques like sliding window, dynamic programming, or binary search. Spotting these quickly allows you to apply proven strategies and save time. It's also important to explain your trade-offs during interviews. For instance, if you choose dynamic programming, explain how it avoids recomputation and why it's more efficient than other approaches. Walking through your solution with test cases aloud not only demonstrates your thought process but also helps you catch potential bugs. Interviewers appreciate seeing how you think and debug on the spot. Finally, starting with a brute force solution and then explaining how you'd optimize it is a great way to show problem-solving evolution. To practice these concepts, consider related problems like LeetCode 198, which focuses on maximizing non-adjacent values using dynamic programming, or LeetCode 53, which introduces Cadan's algorithm for maximum subarray sums. Other useful problems include LeetCode 121, which explores optimal subarrays, and LeetCode 746, which deals with minimizing costs with overlapping subproblems. There are several alternative approaches to solving problems, each with its strengths and weaknesses. Brute force is often the simplest to implement and works well for small input sizes, but it quickly becomes inefficient as the constraints grow. Dynamic programming is particularly effective for optimization problems with overlapping subproblems, though it might require additional space for memoization. Greedy algorithms are another option. They work well when local optimization leads to a global solution, but they're not always applicable and can fail for certain edge cases. Lastly, binary search is a powerful tool for sorted arrays or monotonic functions. However, its effectiveness depends on understanding when and how to use it properly. Each of these approaches has its trade-offs, so it's essential to evaluate which one fits the problem's constraints and requirements best. Thank you for following along. We've explored speculative approaches to LeetCode problem number 2137, emphasizing the importance of pattern recognition and adaptability in problem solving. Stay tuned for more coding tutorials and solutions. Don't forget to like, comment, and subscribe. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!